So, our next speaker is Albert Solana from Qilimanjaro Quantum Tech. So, Albert, welcome. Thank you for being here today. So, whenever you're ready, you can share your screen, and the floor is yours. Okay, Albert, I think that you can share the screen now.
Yeah.
Okay, perfect.
Okay, can you see them? Can you see it?
Yes, we can see it. Thank you.
Okay, sorry about that, and thank you for inviting us, Kilimanjaro, to the conference. I mean, it's really a pleasure to introduce our solution, our current work. I'm Albert Solana. I'm the software engineer at Kilimanjaro Quantum Tech, and basically today's presentation is about the work that we are currently doing. Actually, with a global consortium of several organizations. I'm going to introduce it a bit later to deliver an open source full stack solution named Kibo that actually help organizations such high performance computers, computing centers, and using the quantum capabilities on their needs. And when I show you in this presentation. So actually, let me first briefly introduce the company, Qilimanjaro. We are recently founded startup in Barcelona, which actually is a spin-off of other three institutions: the Barcelona Supercomputing Center, BSC, the High Energy Physics Institute, IFAE, and the University of Barcelona. And our goal basically is to provide an end-to-end quantum solution to our clients, which means that we have people involved in actually quantum hardware, because we are actually building quantum chips, designing, manufacturing them, and performing the control and qubit characterization. And we also have people, actually, another team actually researching and providing our algorithm portfolio that actually takes advantage of our own architecture based on coherent adiabatic quantum computer. And we are going to provide like an end-to-end software solution as a service to the cloud to let our clients use our computing devices and run all our algorithm portfolio. And so, as I already introduced the company, but actually what we are building is this quantum computing that use coherent quantum annealers and based on analog quantum devices that rely on adiabatic model of computation, all based on actually superconducting circuits. That's technology that in this case, we're going to use flux qubits as the key components. And we are actively doing research on that part and using the flux qubit for the adiabatic quantum computation. And on top of the hardware side, we are actually researching on providing quantum algorithm portfolio to exploit actually this technology. So yeah, the idea is that we're gonna have algorithms tailored with this technology, and then on top of that, we're gonna build these end-to-end solutions with several global APIs, so the other clients can connect to our service. And beside that, we also have a service that we provide this service to set up quantum labs from scratch. And we are actually doing that to one of our key partners, the Technology Innovation Institute in Abu Dhabi. So we deliver the Transmon quantum chips with all the lab equipment to be ready to operate with also like a quantum as a service solution. So as you can imagine, and all this infrastructure requires like a framework to operate, and for given like a solution for the internal scientists, but also for the clients outside, and to deliver algorithms. And this is where Kibo, that's like the library that I'm gonna introduce to you, it's where it comes to the scene. So Kibo actually is what we call open source quantum operating systems for quantum programming, simulation, and remote access. And actually we refer it as an operating system in the sense that it covers like the low level of the stack that connects to the quantum chip, where each manufacturer can actually develop their own driver, that we call driver, and they can plug into a Kibo stack, and you can already run algorithms programmed with a Kibo language. It covers the full stack, meaning that you can develop and run your own applications or algorithms, and be accessible for all the quantum devices that are connected to all the Kibo Quantum as a Service platform. Or you can code your own backend because you already have another quantum device and another quantum technology, program your driver, and then connect it to the whole Kibo Quantum as a Service platform. So from the very beginning, I mean, Kibo is being contributed by several organizations. So I mean, it wasn't about one single company. Actually, it was about this whole consortium that actually is being contributed currently by the TII, by Technology Innovation Institute, the Center of Quantum Technologies of Singapore, Qilimanjaro, ourselves, and also the Barcelona Supercomputing Center. And we hope that more is gonna come to contribute to the whole platform. So actually, this is like the several organizations that are already using Kibo for their active research, either institutions, companies, supercomputing centers. So there's a variety of type of users, and that is actually using Kibo, and that's what we want, like having like what are the needs of these different type of users, so then we can also extend and make it more for wider use. And actually, we think Kibo to be used, as we said, like with different several user profiles. For instance, business users who wants to take advantage of the quantum capabilities and connect their applications to the Kibo Quantum as a Service platform and run transparently their solution on the quantum devices. They don't want to exactly to know what are the underlying technologies. They only want to run their application on top of that. So that's one specific users that we are addressing with Kibo. We also have Kibo for developers who wants to actually develop algorithms and need a framework to code them, and devices actually to test and their implementations. So we are providing tools, different libraries, and actually like building a community around them. And also because we are covering actually the whole full stack, we're also addressing this solution to the lab users who are actually building new quantum chips with different technologies, and actually they require low-level framework to help them design and manufacture the chip and also test it with control procedures and characterization and calibration methods to guarantee the qubit quality in that case. So actually, Kibo, in the practical sense, it is like a global platform where users can run their applications via cloud service, a quantum as a service, that process your request and into the desired quantum backend that has its own driver to connect to the quantum chip. For instance, in the current implementation, we have contributions from these organizations that I already mentioned, that actually they are based in different quantum technology, and that's the power actually of Kibo, because it's flexible in the sense that they have a common abstract layer where manufacturers can actually provide their specific driver. For instance, TII has its own transmon qubits, superconducting technology. CQT are based on ion trap technology, and also has started a team to start developing high-performance computing backend. Ourselves, we have transmon qubits right now for gate-based computing, and also like developing, as we said in the very beginning, like the flux qubits for adiabatic models. So we're going to have two different technologies, even for ourselves, and manage it by Kibo. And also Barcelona Supercomputing Center is also developing HPC backend, and also collaborating with CQT. And actually, we also we all are contributing on a quantum simulator. We have like a multi-CPU and multi-GPU support in terms of performance, hardware, efficiency computations, at least on simulators. So then also algorithms can run on this high performance space. I mean, the idea is that any other organizations can work on an application and run using the desired quantum device, or depending on their needs, even build their own driver and extend the supported drivers. Everything is open source, so that the idea is that you can download the code and contribute in whatever part of the full stack that you desire. Like actually any other manufacturer for an operating system. That's why we use that term, because ideally it's kind of the same. We have manufacturers who can deliver drivers, connect to the whole libraries, and everything from above is gonna work exactly the same. So going just a little more in detail, actually Kibo supports several computation backends. We have for quantum simulation with classical hardware, and also quantum hardware, the ones that we call drivers that controls and execute on a quantum hardware. And actually we are active on doing the active development of the Kibo lab code, and it will be actually publicly available shortly. So going into the simulation backends, we have deployed a backend like the basic one on NumPy in the case that you want to run the code either in a small machine, server machine, or even in your laptop, which is based on NumPy. And then other which are focused for classical hardware accelerations, either Kibo TF based on TensorFlow, and Kibo JIT based on Numba and QPy, which has like hardware acceleration and multi-threading and multi-GPU support. That's for simulation, and that's what I was saying. Like we are on currently the development for the Kibo lab, for the driver specifically for the quantum devices that we support. In terms of the Kibo language, computational model, we are supporting algorithms that are gate-based, creating a circuit model such as BQE, quantum Fourier transform, and any user can develop their own gate-based computational models. And actually, we are also supporting Hamiltonian-based models to perform quantum annealing and such algorithm-based like QAOA, and actually more to come. And as an example of new algorithms, actually, when we think of novel algorithms, we can take advantage of the active collaboration of the whole consortium. And actually, we are currently working on designing a federated quantum machine learning algorithms that actually we can train that algorithm separated on each lab, so that the data that have on the lab one leave the local databases, preserving the privacy and security, and then piece together for the final results, and then having like a whole trained model, but using like several quantum computers at the same time. Or even with Kibo, we can perform like benchmarking, like one single algorithm that can run on those several architectures, so that you can compare the results, and that will be like great even for knowing what technology it's best for what specific algorithm, or even hybrid algorithms, mixing like classical and quantum technology built inside the lab, or either using like this simulator or a high performance computing backend with a quantum computer in the same localization, in the same location. So, I mean, there are many possibilities to explore from the Kibo platform, and actually we are organized and with several working groups. I'm gonna explain just briefly them, like a Kibo language to discuss the core Kibo development. We have also like Kibo simulation to work on the simulation backend, Kibo lab actually to share each specific driver implementation and set a common layer to optimize the work, and then each specificities can be described as the driver that has been explained. Kibo high performance computing, to use a supercomputer potential as an additional backend and explore the hybrid algorithms, and Kibo Quantum as a service, because I mean that the end goal is that all possible users or organizations can actually connect to the deployed service and use it. So that's a working group working on that, and Kibo applications, because in the end, want the industry to start working on that. So we're gonna create vertical solutions for that, and there's a working group on working on that part. I mean, so again, it's obvious that obvious to say that you are more than welcome to contribute to any of these working groups. Just contact us and yeah, I mean, let's help grow the Kibo community and actually provide more value to each of us, all of the community. And just as the final remarks, let me say that I mean, we're going to constitute a Kibo Foundation as a sole entity that we actually own the source code, which is under Apache 2 open source license. As I said before, I mean, everything is open source from the very top until the very low when you control the qubit. So that's actually like the innovation that we want to contribute to the, let's say, to the world, in the sense that we're gonna open everything. And then it's easier to let other organizations join forces and contribute to the whole Kibo development in any of the working groups that I just exposed. And yeah, as I said before, I mean, you can contribute because you are building a quantum chip technology and you need the software stack to design and test it, or you are developing an algorithm. What you need actually is either a quantum language to code it, or actually a quantum device to test your solution. So with that, again, thank you for the invitation, and yeah, looking forward to answering any questions you might have.
Thank you very much, Albert, for your interesting talk. So let me check if we have any question from the chat. In the meanwhile, let me ask you, well, a question, probably it's a little bit too technical, but I'm interested. You told us that with Kibo, you can perform some benchmark between algorithm, maybe because you're using different hardwares, for instance. Could you elaborate a little bit more on this point? How these benchmarks are performed, and how do you, visualize the results?
I mean, yeah, I mean, the idea that when we want actually to compare the results either with different technologies, even with hybrid, like when actually the quantum computing makes sense. So in that idea, I mean, the one KPI for sure, it will be like the time that it spends on running that algorithm. But actually, when we are thinking about like large algorithm, there's also like some key KPIs, such as like consumption in terms of electricity, that's also taken into place, and that's also something that we need to start considering. And so we are also like investigating in the terms of giving some other KPI that work on that. Even for instance, in the annealing space, there's also like the coherence, and then it's like, okay, let's build some other KPIs that make sense, and it's not only about time and efficiency, because yeah, I mean, for sure that if an algorithm takes too much, then it's impractical to use. But the idea is like, okay, we have like different machines that we can work and start working in parallel. So working one into the other, then like helping the quantum devices and the classical devices all in the same laboratory. Okay, how we can build these other KPIs. So in that sense, yeah, we are creating new KPIs, and I mean for now the ones that we have, we are just comparing that. Okay, the efficiency is in time. So when we run a quantum fermion transform, then the idea is like we are just comparing the time that running into a simulation with the different backends that I exposed, but also in the quantum machines that are like building like several releases or evolution of our quantum chips. But so yeah, I mean, for now it's this initial KPI, but as the, let's say, the complexity increases, yeah, I mean, for sure, like the power consumption is gonna take into a place, and especially on high performance computers in super centers. So then, yeah, I mean, data centers are spending a lot of energy, and in that case, there's some orders of magnitude that the quantum computers can also benefit using that. So I mean, for sure that is going to take into account for the future KPIs.
Thank you very much. It was really interesting, Albert. So thank you very much for joining us today. So thanks a lot.
Yep. Thank you.